Questions? Meaning that there are one N1 another 2N2 times Q, another N1 N2 times. That is just a particular identification that we are doing.
Yeah. You could use some other identification. But this will be useful when you try to develop this field theory idea. Right? That's why we use this. But at this level, when you are trying to glue into Riemann surfaces, you can use any other function that relates omega to the W2 and W1.
This notion that if we go into one, we go out of one, that is a particular convention. It's a particular gluing.
Yeah, yeah, because you cut out some disks near each center, right? And then you say that you glue them, which means that as you go into this disk, right, what you do is that you emerge out of that on that side. Right? So that property has to be obeyed. Right? That as you go inside this disk, you should come out from that disk. Right? Otherwise, you start gluing. Right? Okay, but otherwise, you can change the function relationship. Are there other questions? So last time we introduced the idea of this plumbing fixture, which is gluing two Riemann surfaces into a third one of higher genus and higher number of functions. And what we saw is that we can, if we have a section, so we had two, we started with PG1N1, PG2N2. Now imagine that you have some section in PG1N1, you have another section in PG2N2. So first we saw that given a particular point here and a particular point here, which means given a particular Riemann surface of genus G1 with N1 punctures and another Riemann surface with genus G2 or N2 punctures, there is a notion by which you can glue them together. So this is sigma G1 N1 and this is sigma G2 N2. We can glue them together to produce a new Riemann surface of genus G1 plus G2 and N1 plus N2 minus 2 punctures. Okay, two punctures go away because we cut out small disks around each puncture and then glue them together by the appropriate identification. But what we saw was even more that for this family, okay, which is a section, when you glue them by this clubbing relation, by the relation that the local coordinate around the N1 puncture on the first surface and around the N2 puncture on the second surface is equal to Q. Then by varying Q, okay, Q is a complex parameter, so it has two real parameters. Then by varying Q, you can actually generate a section of P G1 plus G2 N1 plus N2 minus 2. Okay. And we saw this by parameter counting. Okay. This family over here has 6G1 minus 6 plus 2N1 parameters. This family over here has 6G2 plus 6G2 minus 6 plus 2N2 parameters. And then we get two more parameters from Q. And this is 6G1 plus G2 minus 6 plus 2 N1 plus N2 minus 2, which essentially has the right number of parameters that is required for getting a section of this. We also saw how to construct the corresponding measure on this. So what we had found was that if we try to construct, for example, omega 6G1 plus G2 minus 6 plus 2 n1 plus n2 minus 2. Okay, so this is the particular form that you have to integrate over this. These will have several tangent vectors. Let's call them v11 up to v1 6 minus 6 plus 2n1. So these are the tangent vectors that come from the tangent vectors of this section over here. Okay, this is 6g1 plus 6g1 minus 6 plus 2n one dimensional space. So there are those many tangent vectors that is induced from here. Then there are tangent vectors corresponding to del q and del q bar. And then there are tangent vectors v2 1 to v2 6 v2 minus 6 plus 2 v2. So these will be given by the following correlation function. So first of all, you have to put v1 up to vn1. Sorry, v1 is 1 up to v1. Then you have to put, I'll write down the expression for bq and bq bar shortly. Okay, the two b's correspond to this tangent vector, and then you have b v2 1 up to v n2. And then of course you have to insert the external vertex operators. So the external vertex operators, let me write as 1 to n1 minus 1 u1 I so that I equal to 1 n2 minus 1. Okay, let me write the bq and bq bar expression and then I'll go back to that formula. So bq was minus 1 over q this contour is to be taken with sigma g1 n1, right? And dq bar was minus 1 over q bar. Okay. So pictorially, let me just explain what is happening here. So what we had was two Riemann surfaces. With various vertex operator inserted at the vertices. And then there are two spatial punctures. N1 is punctured here and N2 is punctured there. Okay. So what we did was that we cut out a circle around each. This circle, if W1 N1 is the local coordinate around here, then this circle is at mod W1 n1 equal to mod q to the half. Q is some complex parameter. This circle is at mod w2 n2 equal to mod q to the half. And then we group this circle with this circle by saying that w1 n1 w2 n2 is equal to q. Okay. So as you go into this circle from this side, here you come out of this circle. Okay. That's the sense in which you have to look at. And what this formula tells us is that if we had a section for this, which means you had a choice of local, specific choice of local coordinates around each of these punctures, then after gluing you get a section of the bigger space Pg1 plus G2 N1 plus N2 minus 2, and the corresponding region that you have to integrate over there will now be given by this. Okay, and the main analysis that we did last time was to derive these factors BQ and BQ bar. Right? These are the B's that you have to insert correspond to tangent vectors del del Q and del del Q bar. These are of course induced from the tangent vectors of the original surface sigma G1 N1, and this is from the original surface sigma G2 N. Okay, so this is where we had arrived roughly last time.
So what about the normalization?
Oh, normalization, here you are right. So normalization here will be, let me write, minus 2 pi I to the power, the corresponding normalization for this, okay, which is 3 minus 3 G1 plus G2 plus N1 minus 2. Okay, so this is the normalization for this measure omega. Is this okay?
And this is same as before your earlier.
Yeah, this is same as the earlier expression, except that last time probably I didn't write all these factors explicitly, right? Because you focus basically on deriving this. Right? But these are just induced from, because these are the tangent vectors. So the tangent vectors of the section that we get, right, can be divided into three classes. One class is the tangent vector that is induced from the Pg1 N1, right? There is a section in Pg1 N1, right? That has certain tangent vectors. Those are still parameters that are labeling the new section. So those tangent vectors are here. Then the tangent vectors of Pg2 N2, the section in Pg2 N2, those are here. And these are the tangent vectors for del del Q and del del Q bar. These are what we derive explicitly by looking at how the gluing function changes, right? By the usual procedure that we change Q to Q plus delta Q, and then determine how W1 new is related to W1 old. And that's told us that the precise tangent things that you have to insert are these combinations.
So that should be minus 3 minus 3 G1 plus G2 minus N1 plus N2 minus 2.
Yes, right. Minus. So our goal today will be to try to take this expression, okay, which involves a correlation function on a Riemann surface of genus G1 plus G2 and a N1 plus N2 minus 2 punctures, and re-express this in terms of a correlation function on a Riemann surface of genus G1 with N1 punctures and a Riemann surface of genus G2 with N2 punctures. Okay? So, the correlation function of this on this bigger surface you have to express on this surface of higher genus, you have to express in terms of correlation functions on surfaces of lower genus.
So when we calculated
Yes.
that number 6 minus 6, then
Yes.
to get to the bigger surface. Means add 2 more degrees of freedom to get to the bigger surface.
Yeah, 2 more meaning the 2 parameters came from Q.
Yes, sir.
Right? So total number of parameters that is leveling, that are leveling the section of this bigger space, right, are the parameters that were there for Pg1 and 1, right? The parameters that were there for Pg2 and 2, and these 2 extra parameters that come from Q.
Yes, yes. So we have to introduce 2 extra parameters to account for the total number of parameters
Exactly.
for the bigger surface.
That's right.
Can we write this the bigger surface amplitude in terms of the small one if we have to add 2 more parameters?
Yeah, we'll see. Well, the 2 more parameters has gone into this B, right? BQ bar, right? And we'll see how to deal with those. Okay? So right now we have a correlation function here, right? And you want to express it in terms of correlation functions of lower genus surfaces, right? Let's see if we can do this.
If we did the doing differently, the definition of this BQ, whatever would be the counterpart, then that also would have differed.
Yes, exactly. If we had used a different doing function instead of W1, W2 equal to Q, right, I could have used some complicated functional relationship between W1 and W2. What will change are these. BQ bar will change. You still need 2 parameters because otherwise you will not get a section of the final Pg1 plus E2 and N1 plus N2 minus 2. So you take a 2 parameter family of doing functions, okay? But for those 2 parameters you again have to derive what the corresponding insertions should be, okay? And those will be different. That's referred to as parameterizing the new section. Okay, so now let me define the following quantity. So let's say sigma 1. So let me start with let's start with this guy. Okay, this is a correlation function on a genus G1 Riemann surface with L1 punctures. It doesn't know anything about larger genus C2 surface. Now, N1 with puncture is somewhat special because that's what you will do. Okay, so let's give it a special treatment. N1 is punctured, the state that is being inserted, we are calling it A1 N1. Now, notice that this quantity is linear in A N1 N1. If we take a linear combination, if we replace A N1 N1 by alpha times a vector, a state times beta times another state, it will be alpha times that correspond to first amplitude and beta times the second amplitude. Okay? So it's linear in A N1 N1. This allows us to write this defines sigma 1. We define a state sigma 1, which is a very complicated state in general. Okay. But there exists a state sigma 1 whose inner product with A N1 N1 will give rise to this correlation function. Okay. This simply follows from the fact that it is a linear function of A N1. And this will take to be the BPZ inner product. Okay, the same BPZ inner product that we introduced earlier. Okay, and the corresponding operator, once you have a state, okay, in CFT there is a state operator correspondence. Okay, so the corresponding operator will call corresponding operator will call sigma 1. Okay. So sigma 1 is by definition this object. Okay, I, if you recall, is the transformation I of z equal to minus 1 over z.
I can find that sigma 1 for any definition of inner product, right? We are just choosing diffuse.
Yes, we can take sigma 1 for any definition of inner product. As long as it's a linear, right? It's a linear product, it's a linear function of A1. Right? It has to be non-degenerate. Right? The inner product that we use has to be non-degenerate. Okay, so that you can invert, right? Because what is given in the is the left hand side. Yeah? And you are saying that there is a unique sigma 1 for this holds. This holds for every possible choice of the vertex of part A and 1 and 1. Okay? This is an identity, so this defines sigma 1 irrespective of what state you choose here, right? This has to hold for every choice of state A and 1 and 1. A 1 and 1. Similarly, if we have this object, this we will call sigma 2 A 2. Okay. So let's try to interpret what we have done. So here is a complicated correlation function. A n1 is inserted in the coordinate system W1. What you are saying is that this complicated correlation function can be reinterpreted as a two-point function on the sphere of A n1, okay, say inserted in the coordinate W1, and then sigma 1, which is I dot sigma 1, right? So this can be interpreted. So this sigma 1, let me write it here, A1, A1, and interpreted as I dot sigma 1 of 0 times A1 of 0. These are in the W1 coordinate system. This correlation function is calculated in the W1 plane. W1 in 1 plane. Okay, A1 in 1 is inserted in the W1 in 1 plane, right? That's why you are not transforming it by anything. Right? So if you use the W1 in 1 coordinate, then this complicated object here has a simple interpretation in terms of a two-point function on the sphere. Of course, all the complication has gone into the definition of the state sigma 1. Right? So it's not that we have simplified the calculation of this itself, okay, but we just interpret this.
So this correlation function, this is calculated on sigma g1 n1 or sphere?
No, on sphere. Because this represents inner product with the two-point function on the sphere.
Yes.
Right? The left hand side is calculated on the sigma sphere. Okay. This is calculated on two-point function on the sphere. Right? On the W1 N1 plane, right, we are just calculating this two-point function. Is this clear?
So the rest of the information is in sigma 1.
Rest of the information is sigma 1, right? We keep sigma 1 as a complicated state, we don't worry about what it is right now. Similarly, sigma 2 with A2 and 2 is I dot sigma 2 of 0, A2 and 2, 0. This is, here it's in the W2 into 2. Okay, of course, the actual value of the correlation function doesn't care about what plane you are using, right? It's just in some plane. But I have just written this explicitly to denote that it's in the W1 N1 plane that the coordinates is the field A1 N1 is inserted in that coordinate system, W1 N1 coordinate system, right? That's why I have not used any F dot anything, right? This is identity. This thing similarly here is identity W2 N2 plane. Now suppose you want to see the effect of gluing these two surfaces. Okay. Now the gluing is done by gluing W1 N1 with W2 N2, right? With the identification that W1 N1 W2 N2 is equal to Q. Okay. So this was in the W2 N2 plane, this is in the W1 N1 plane, and now you are gluing these two. Okay, so these are gone. Okay, we have cut out discs around this and we are gluing them. So let's see what this is telling us in the W1 N1. Okay, let's just convert this whole thing in the W1 N1. Okay, what is the effect of the gluing? Okay, after the gluing. So the glued surface in W1 N1 has two insertions. One is sigma 1. Sigma 1 is inserted in coordinate, local coordinate. Okay, let's just call this W1 such that W1 N1 is equal to IW1. How do you know this? It's I dot sigma 1, right? So in the W1 N1 plane, the local coordinate in which sigma 1 is inserted is related to the global coordinate W1 N1 that we are using by this relation. Okay, originally this was the yes.
Sorry, W1 is the coordinate of what?
This is the local coordinate of sigma 1. The local coordinate in which sigma 1 is being inserted. You see here, look at this two-point function, right? What is the interpretation of this two-point function? It's a two-point function on a sphere, right? A1 N1 is inserted in a local coordinate, which is W1 N1 itself.
Yes.
This is inserted in a local coordinate. Okay, if you call that local coordinate W1, then that W1 is related to W1 N1 by this relation. Then that's why it's I dot sigma 1. Is this clear? That's what I have written here explicitly. Now, what is the other vortex of party that is inserted in the W1 N1 after doing? These two have gone, right? But now this vortex operator, right, which was earlier in the second surface, now they have been glued. So this can also be now retranslated as some insertions in the W1 plane, W1 N1 plane. Is this clear? Okay. So sigma 2 is inserted. Yeah.
The second amplitude now that means omega 1 and omega 1 N1 and omega 2 N2 are identified with this relation.
Yes.
We'll just do a coordinate of omega N2 to omega 1 to.
Yeah, so that's what we'll do, right? So let's say sigma 2, so the second insertion, first one is sigma 2 insertion. Okay. Suppose this is inserted with in local coordinate. W2. Okay? Let's say W2 is the local coordinate of sigma. Now, from this we know that the relationship is W2 N2 is equal to I of W2. Right? Because in W2 N2 coordinate system, this is inserted directly in the W2 N2 coordinate. This is inserted with an I dot sigma 2, which was in that coordinate system. the local coordinate of this related to W2 and 2 by this function. Okay. But now we are expressing everything in the W1 N1 coordinates. Right? So in the W1 N1 coordinate, this is related to the W2 by, this is Q over W2 N2. So this is Q over IW2. So this is minus Q times W2. Right? Where IW2 is minus 1 over W2. Is this clear? So the glued amplitude has the interpretation of a 2-point function on the sphere with 2 insertions. One sigma 1 insertion, the other one sigma 2 insertion. If W1 and W2 are the local coordinates of sigma 1 and sigma 2 insertion, then the global coordinate W1 N1, which I have chosen to be W1 N1, is related to W1 by as W1 N1 is equal to I of W1, and is related to W2, which is the local coordinate of sigma 2, as W1 N1 is equal to minus Q times W2. Is this clear? Okay? It's just a 2-point function on the sphere with 2 insertions of sigma 1 and sigma 2 in appropriate coordinates. So let's call this f of it. Okay, this is the definition of the function f.
And so, due to this gluing, what compensated for this, where did the information about A1, N1 and A2, N2 went?
They went there because you have the gluing, right, removes those what state has been inserted or those punctures have been removed, right? Right? So those are gone away, right? Only information that remains is the local coordinates. The local coordinate of the function that we have used. Right? That is important because that coordinate system W1 N1 is what we are using for making this function identification. Okay? These coordinates of pointers are gone away. Because originally you had an N1 point function, right? Now one of the things which have been inserted, right? There is no information about that vertex of point because that is not even there as part of the new correlation function. Is this clear?
Ultimately, we will calculate the correlation function sigma 1, sigma 2 like that. Eliminating the states in between.
Yes, exactly. That's what we will do. Okay, so let's see what we get. So the glued amplitude will be I dot sigma 1. I am writing everything in the W1 in one plane. Okay, but you could have equivalent written as W2 into plane, it will make no difference. I dot sigma 1 0 and then F dot sigma 2 0. F is this function over here, right? Because sigma 2 is inserted in this coordinate system. And this, in fact, we can also give a conformal field theory interpretation. It's sigma 1. And this transformation f dot sigma 2 of 0, what does f do after all? It just scales by minus q. Right? So this is minus q to the power L0 minus q bar to the power L0 bar sigma. Okay, if q had been 1, or if q had been minus 1, then this is just identity. Right? You will get the definition of sigma 1, sigma 2 in the product. Right? Because of this transformation by f, you just have to put it inside this minus q to the L0 minus q bar to the L0 bar.
I'm a bit confused. This is which generally?
This is the amplitude of the on the glued surface. Right? A set of b1s, a set of b2s, whatever operators you had on sigma 1, and whatever operators are on sigma 2, right, have been put, except that the vortex operator at the N1th function of the first surface and the N2th function of the second surface have been removed, right, and their amplitudes have been grouped.
So sigma 1 and sigma 2 knows about the rest of the
Exactly.
thing.
Yes. Rest of the N1 surface as well as what operators you had inserted on those N1 surfaces.
Yes. Can you repeat the information of AN1 and AN2 what later was asking the same question?
Yeah. So the point is the original amplitude, right? Sigma 1 A N1 was given by this product, right? Product over B V1, right? And product I equal to 1 to A1 I. Okay? This was the definition of this, right? But sigma 1 has no knowledge about A1 N1. That just this is supposed to be valid for all the possible choices of A1 N1, right?
Yeah.
So the definition of the state sigma 1 doesn't know anything about A1 N1, right? It knows about everything else. It knows about the insertions of these B's and it knows about the insertions of these other AIs. Similarly, sigma 2 doesn't know anything about A2 N2. Okay. Now what did I do? I took this sigma 1. Okay, this now I will reinterpret it as a 2-point function on the sphere with sigma 1 inserted here and A1 N1 inserted here. This one, the other one I inserted again as a 2-point function. Okay, with sigma 2 here and A2 N2 here. I cut out this over here and glued them. Okay, but this then has an interpretation that this was the correlation function that we are trying to calculate originally, right? Because after all, this one is the same as this Riemann surface amplitude, right? So I have just used the W1 N1 coordinate system, right, which is common between here and here. I have just cut out this and I have glued it with this, right? Sigma 1 is a complicated state that carries the full information about the rest of the Riemann surface, right? So whether I do it at this level or this level doesn't matter, right? The gluing should produce the same amplitude. Okay. So I was supposed to glue two Riemann surfaces with these discs cut out, right? Instead of that, I glued two spheres with the discs cut out, right? But this sphere contains complete information about this Riemann surface, and this sphere contains complete information about this Riemann surface. Right?
So in that expression, AN1, AN2 are not there simply because the full Riemann surface, in the full Riemann surface, those two vertex operators.
Exactly. Those two vertex operators are not there, right? So those vertex operators. So this amplitude knows only about sigma 1 and sigma 2, which means every operator that has been inserted outside this disk, right? The B's as well as the A's, right? And every operator has been inserted outside this disk. But the vortex operators here and here are gone. Okay, and it's also obvious from here that the definition of sigma 1 doesn't know about A1N1, right? If A1N1 was an auxiliary construction that was a state that was used to make sense of this equation, right? But sigma 1 as an abstract state, right, has no dependence on this. Right? This is supposed to be valid for every choice of A1N1. Okay. So the claim is that this is the amplitude that you will get by gluing these two. Okay, gluing into original Riemann surfaces. Okay. Now I have written it as a 2-point function on the sphere, but all the complication has gone into the sigma 1 and sigma 2. Yes.
So, counting this thing, these BDIs are the insertions on the Riemann surface of genus G. They are
Yes.
Riemann insertions.
Yeah.
Now, this expression that you have written down is actually a contraction of the volume form with these vectors, right?
Yes.
So, the number of vectors is much larger than the number of B's, the tangent vectors to the moduli space, right?
Number of vectors,
I mean,
not much larger. I mean, I have base 2 so far.
No, this B are B V1 to B Vn1 only, right?
These V's. But on the sigma 2, there are B V1,
That is right.
B2 to.
Yeah, but the moduli space dimension has additional 6G1 plus G2 minus 6 factor, right?
So these V's are providing for that, right?
So here that number shouldn't it go to with that T?
Should be
No, this is on a bigger, higher genus one surface. Right?
Yeah.
So on this surface, right, the number of B's that you need is precisely this. Right? This gives you 6G1 plus.
So that one should go to
N1 should be
Six
N1
G1
minus
is
C.
G1.
This one.
No, that
N1 should be
Oh,
6
no,
minus
yeah,
C.
yeah.
That should be 6 G2 minus.
Yeah, this 6G1 minus 6 plus
yeah, that was the question.
2. Yeah. And this is
6G2 minus
6G2 minus 6 plus 2.
and the same carry over then everywhere like that.
Yeah, so all of these are about those values.
Yeah.
Okay. Still, I have shifted a little bit because what you want to calculate is this object, right? There's BQ bar sitting there, right? That I have not included. In the definition of sigma 1 and sigma 2, I just used this part and this part. I didn't say anything about this. But this, in fact, you can include in the definition of either sigma 1 or sigma 2. Okay? Because when I said the sigma 1 is given by this, right? I could have also used the BQ bar inside this. Right? Nothing would have gone wrong. It's just they will float around the definition of sigma 1. Is this point clear? Okay? The definition of sigma 1, instead of just saying that this includes only the BVs, I could have also inserted BQ bar. Okay? Or I could have done it for sigma 2. It doesn't matter. So let me now be more accurate for what we want to do. Okay. Let's not try to take the definition of sigma 1. So let's define sigma 1 tilde. This time by including that extra factor. This goes, I goes to 1 to 6, U1 minus 6 plus U1, BQ bar. Okay. Then the desired amplitude is sigma 1 tilde
BQ and BQ bar, we are just putting that information by hand.
I just redefine my sigma 1 tilde okay, to include BQ bar in the product. Okay. See, I mean the problem here is that if we just had this quantity, right? This quantity, right? Here we include sigma 1 and sigma 2 with all these B insertions, but the BQ and BQ bar were left out. Right? But we really want to get to this amplitude, right?
Yes, yes.
With the BQ and BQ bar included. Right? So I define the sigma 1 tilde whose definition includes this BQ and BQ bar. Right? And then if I repeat the same logic, right, and calculate instead the relationship between sigma 1 tilde and sigma 2.
But in deriving this relation, here you started with the amplitude of the Riemann surface sigma g1 n1 and sigma g2.
But I didn't say anything about what operators have to be inserted, right? The fact that I have to insert precisely those B's was never needed. Right? The definition of sigma 1, right? Some operators are inserted.
Yes, that won't be needed because these q and q bar are the two extra parameters that I am including when I am talking about the.
Yeah, but the Q and Q bar hasn't even come in at this stage. So look at this analysis, right?
Yes, okay.
This analysis simply tells us that suppose we had some Riemann surface with some set of operators, right? Need not even be B's or the A's, right? It could be some complicated operators on that side, right? I just define sigma 1, the state sigma 1
That will be like this.
by this relation, by a similar relation over here, right? Whatever operator you insert here, right? I need it for the capital B's, right? That's why I defined this. But I could have taken any product of operators here.
Yes.
Okay? And if you want to glue the two Riemann surfaces with those operators inserted, this general formula will still be valid. Right? The fact that I use precisely the B of Vi's and these or the A1i's of the specific A1i's that we are interested in, that's completely up to us. Right? We could insert whatever operator we need on the first Riemann surface. We could insert whatever operator we need on the second Riemann surface. Right? Define sigma 1 and sigma 2 accordingly. And then carry out this analysis. Right? What this will give now is a correlation functions where the operators inserted on the first Riemann surface are there on that side. Operators inserted on the second Riemann surface are there on that side. But the two Riemann surfaces in the middle has been glued to make a single Riemann surface. Is this point clear? So again, let me emphasize the general feature is that given two Riemann surfaces, okay, with some arbitrary operators inserted on the Riemann surface, right? Doesn't have to be B's or B's or anything, right? I mean, it could be the C host, for example, right? For some reason, if you want to read the C host, okay, some operator inserted on the first Riemann surface, some operators inserted on the second Riemann surface, and you are trying to glue them together. Okay. We define the state sigma 1 by including whatever operators you want to include. Okay? The definition of sigma 1, like this. We have defined sigma 1 tilde by including this additional operators. Similarly, I define my state sigma 2 by including whatever operators you insert on the second Riemann surface. And then you carry out identical analysis to what we did. Okay? We will arrive at this expression over here. And this will describe the corresponding glue dimension.
So when we perform this integral, we have to do the integral over dq by dq bar.
Yes, eventually. Right? Right now we are doing the integrand.
Yeah.
Right? Eventually we will integrate over dq bar. Yes.
Yeah. So what is the invariant measure? I mean, is there some factor to that dq by dq bar? Because you can choose any function of q over here, right?
No, because I am giving you a form, right? Because I am giving a form, there is the measure is completely fixed. This form you integrate, right? So there is no ambiguity in carrying out the integral anymore. Because I have given you how to contract the tensor, the P form, that a particular form with del del q and del del q bar, right? So dq is dq bar will be multiplied by this form, by this contraction.
This whole thing will be very difficult.
Exactly. So the whole thing will be invariant under the reparameterization of q, right? If we reparameterize q, the dq is dq bar will change, but the form will also change accordingly. Is this part clear? Yes.
But, so the inner product that you have written here, you cannot, between sigma 1 tilde and an 1 1, you cannot write it as a form contracted with some other vectors now.
Some other vectors?
So you cannot use the same form as before to define this inner product here. So the form on sigma G1 and 1.
Yeah, see at this stage, we are not even thinking of this as a form, right? The form will come only when you reinterpret this as an integral over, that will integrate over q and q bar, right? At this stage, all I am saying is that think of this as a number.
Yes.
So you have to choose a specific parameter, think of this as a number, and this number, okay, you think of the right hand side as a number, and my definition of the state sigma 1 tilde is such that this inner product gives you that number. So that gives the state sigma 1 tilde.
Okay, So we don't try to relate this anymore to the amplitude on sigma G1 and 1, but we just use it to define sigma 1 tilde.
Yes, exactly. And then the claim is that if we now calculate this object, this will give the amplitude that we want here. Right? And this then will integrate over the full moduli space, right? The whole section. Exactly.
Here in a moduli space point, specify that q and the rest of the thing. Then the endpoint function is given by that what you call desired amplitude.
This one, yes.
Yeah. This amplitude is what then? This represents what? What you
Well, this doesn't represent anything specific, right? I mean, sometimes you may want to get something which is not a form, right? Not a form over the entire moduli space, right? But a form of degree 2 less, right? See, I defined omega p for all p, right? Right? So you could try to contract omega, okay, of 6g minus 6 minus 6g minus 6 plus 2n minus 2 form with a set of tangent vectors without a del deltas. Right? Then the BQ bar will not be there. Right? So this will represent that, but right now it doesn't have any ability.
It's not physical amplitude, it's some mathematical quantity.
Exactly, it's a mathematical quantity which may be needed for various manipulations. Right? I mean, that's why I defined omega p is for general p. Right? But right now this doesn't have any physical interpretation. Okay? But it can be defined nevertheless. Okay? Because let me again emphasize that this sigma 1 and sigma 2 can be defined with any operator insertion that you like. Okay? It doesn't have to be the b's or the ai's. Right? The fact that I define sigma 1 is just like here sigma 1 tilde a1 n1, right? These are some operators I have chosen. If I didn't know anything about those, okay, I could have still defined this by choosing some particular operators here. Okay? As long as it involves say a1 n1 insertion in some specific coordinate system. Okay? This is well defined. Okay, and you can then strip off this a1 n1 to define a state sigma 1. Right? That's all we need for this construct.
What will be the analogous construction for the other kind of gluing where we are gluing the two punctures of the same Riemann surface?
It will be similar, right? I'll comment on that at the end, right? Once we get the final expression, then we will see what the analogous construction will be there. Okay? You cannot write it as an inner product between two objects, right? But the final expression, right? Once you arrive at the final expression, then it will become clear what the corresponding amplitude will be.
By this prescription, whatever amplitude we calculate,
Yes.
this number is not 6 minus 6, g1 plus g2 will be this whole amplitude, this is the prescription.
Well, I mean, you can always, this is well defined. Whatever operator we insert here, right? It will give a non-zero result.
No, I'm saying for the final amplitude.
This amplitude. Yes.
As long as the ghost number is not 6 minus 6, g1 plus g2,
Yes.
this amplitude will vanish.
Yes, it will. Well, if you think of the ghost number of sigma 1 tilde and sigma 2, this is a 2-point function on the sphere. Right? So then the total ghost number should be equal to minus 6 or 6.
Yes, for sigma 1, sigma 2, since it's on the fields.
Yes. Total ghost number of sigma 1 tilde plus sigma 2 should be 6.
If you write the sigma 1 explicitly, if you write the sigma 1 tilde in that form,
Yes. So you have to count the total ghost number of sigma 1 tilde. Right? And you will find that as long as this amplitude is non-zero, right, this will also be non-zero. The ghost number should add up correctly to 6. Okay, these B's will essentially provide the necessary ghost numbers. Okay, now one more step that will simplify things a little further. The claim is that sigma sigma 1 tilde A1 N1 can be written as 1 over Q Q bar okay, because definition of sigma 1 didn't have a BQ BQ bar.
There is some BPZ conjugate has to be done right over here because sigma 1 and sigma 2 both were, I think it's.
Yes, BPZ conjugate has been done in some sense, right? Because W1 W2 equal to Q involved a BPZ conjugate, right? That's why sigma 2 came on the right hand side. If you go through the analysis, right? Sigma 2, so in the original amplitude, sigma 2 was always on the left, right? So they are at infinity. But because W1 W2 equal to Q, if the W2 equal to infinity came down, W1 equal to 0. And that's why it is sigma 1 tilde and sigma 2 on this side. Right? But to begin with, indeed, both sigma 1 and sigma 2 are on the left.
So in some sense, the choice of the inner product dictates how we should glue the two local coordinates?
Well, choice of the inner product is BPZ conjugate. Right? That has been defined once and for all.
Right.
And if we use this gluing condition W1 W2 equal to Q, then the expression is simplified.
Right.
Otherwise, it will be a more complicated transformation. Right? The fact that this function f of W came to be just Q multiplication by minus Q. That was because the choice of the inner product was by BPZ conjugate, was by this I. And W1 W2 equal to Q is also essentially relation by I up to the scaling by minus Q.
So otherwise it would have been some general f of Q.
Exactly. Otherwise it could be some more complicated f of Q, right? Which will be hanging around. So instead of having just simply Q to the minus Q to the L0 minus Q bar to the L0 bar, you have a more complicated transformation. Okay, that's why W1. So inner product we always use BPZ, right? But you could have asked what happened if we had used not W1 W2 equal to Q, but some more complicated relation, right? If we had used a more complicated relation, then if you would just follow the same steps, these transformations will be a more complicated transformation. And the local coordinate choice of the second insertion, right, in the W1 coordinate will be more complicated. Okay, now how do you prove this? Okay, it's not actually very hard. Is inserted at W1 N1 equal to 0. Right? A1I in this relation is A1I at 0. This is at in the W1 N1 form. Right?
So we A1 A1 0.
Yeah, A1 N1. And then the B's, BQ was 1 over Q times integral to the overall gap minus sign. Okay, BQ bar. So minus sign actually doesn't matter because both BQ and BQ bar has a minus sign, right? So there. Now this operator, so the picture of the Riemann surface is that we have a vortex operator here and we are integrating these B's around this vortex operator, and then the rest of the stuff is somewhere there. So when you apply B, so similarly for BQ bar. Okay, BQ bar is the same thing with complex one. So as an operator, if you take BQ bar on the operator A 1, then 1 at 0, the corresponding state A1 N1 of 0, of course, is at a state A1 N1. Okay, that becomes state A1 N1. Okay. And you can easily see that BQ bar, which will be the corresponding thing with this bar, that's nothing but B0 bar. And BQ is B0. Okay, 1 over TQ bar I have to put. Yes, because that's these factors over here. So BQ bar insertion here can also be reinterpreted as that you take the state A1 N1 and don't use A1 N1, you replace it by a new state or new vertex of order whose state is this one. 1 over TQ bar times B0 B0 by A1 N1. Is this clear? This is B0. Is that clear? If you look at the expression for B0, yeah, if you use Bn as sum over or B as sum over Bn W2 minus n minus 2. Okay, B0 is exactly this integral. Okay. For example, if you had a C bar in the vertex operator, say had a C0 bar on something, then you can check that this will precisely remove the factors of C0 bar or the vertex operator. Pardon? Suppose the vertex operator, suppose A1 N1 has found C0 bar on some field. Yeah. Okay, so so if this is the state, then as a vertex operator A1 N1 will be del C del bar C bar on the end. C0 is created by the operator del C. Okay. Now you take this integral, pick up the BCOP, right? BCOP will give rise to 1 over z minus w square, and you can check that the effect of this integral will be simply to remove this del C and del bar C bar. Okay, which is exactly what B0 bar will do. Okay. So this relation basically follows from this, because what we are saying is that instead of taking this BQ bar, here I could just simply remove BQ bar and replace the A1 N1 here by B0 bar or A1 N1. Okay. So removing this takes us to the original definition of sigma 1 N1, sorry, sigma 1, okay. But it changes the state A1 N1 to B0 bar A1 N1, and that's what will happen. And 1 over TQ bar comes because of the definition is also 1 over TQ. So now we are getting there. So we get the integral on the glued surface is minus 2 pi I to the power minus 3 minus 3 plus 3 by 3 minus 3 g1 plus g2 minus n1 plus n2 minus 2 times sigma 1. Okay, so this implies also that sigma 1 tilde is 1 over q bar sigma 1 is equal to 0. Right? Because if this is true, okay, we proved this bar is showing that A1 gets replaced by B0, B0 bar A1. But once you have this as a state, as a inner product relation, you could have also thought of as B0, B0 bar acting on sigma 1 on the left, and you get a relation of this kind because this, the top line holds for any choice of A1. So using that, we can write this as sigma 1 B0 B0 bar minus q to the L0 minus q bar to the power L0 bar sigma 2 times q bar inverse. Is this okay? I just rewrote this. Okay, this was the amplitude, but I just inserted this B0 B0 bar.
Is this 1 over Q?
That's Q bar inverse I wrote. Okay, that's 1 over Q bar. Okay. And let's now write the form. This is the form. So d omega m1 1 weight d m1 6 d1 minus 6 plus dn1. So these are the parameters that label the section on the original sigma 1 g1 n1, sigma g1 n1, then weight dq, weight dq bar, weight dm2 1, weight dm2 62 and 6 plus dn2. Okay, this is what we need to indicate. If you change the parameterization here, okay, what is going to change is that this v1 1 to v1 6 v1 minus 6 plus 2 and 1, those will change, right? And they will change precisely to compensate so that the integration, so that the integral remains invariant. Okay, that's the advantage of using a form, right? Form can be integrated over a surface, okay, over a subspace without specifying any additional data. Okay, now we still haven't done what you wanted to do.
Sir,
Yes.
this is being integrated over this modulus space or section of P.
Well, section of P in the sense that these are the abstract parameters, right, which you can take to label the moduli space. Okay, but so let me draw this again. This is P, right? Pgn. Okay, where G is G1 plus G2 and N is in 1 plus N2. So this is our MGN. Okay, and we have chosen a section. Section means what? Like for every point in MGN, you have chosen some specific local coordinate system at the punctures. Okay. Now, this section can be labeled by the coordinate of MGN. Okay. So you can take that as a parameter. Coordinates of MGN.
Then here something should know about those sigmas will know about local.
Exactly. Sigmas will know about the choice of local coordinates. Right? Because sigmas involve the insertions of all the other AIs. Right? And those AIs A11 to A1N1, those are inserted using the local coordinates specific to the original choice of the section. Okay, are there other questions? Okay. Now the point that I was trying to say is that we haven't yet solved the original problem, because what did we ask, what did we set out to solve for? We had this big correlation function on the blue Riemann surface, right? We said, is it possible to express this as in terms of correlation function on the smaller Riemann surfaces? Okay. Now that you haven't done so far, right? Because you still have a correlation function, right, involving both sigma 1 and sigma 2. Right? It's not individual correlation function of small advance. Okay. But once you have written it as a state like this, okay, now we can do the usual manipulation involving completeness. So what we are going to do now is to insert a complete set of states between these big states. Okay. So we write this, we write sigma 1 B0 B0 dot minus q to bn0 as sigma 1 phi m c Okay, so this is an identity where you have used completeness, and this is another identity. Okay, except that here you have to include minus 1 to the power g. Okay, that g is the Roche number of phi n c of phi n. Okay, because this we have seen earlier, right? That if this is identity, okay, then phi n c phi n, okay, is not identity. You have to introduce also this minus 1 to the g factor, because the inner product is not completely symmetric, right? Inner product, it's a minus 1 to the n, minus 1 to the g factor if these have got both.
So it's phi n c phi n or phi n c?
No, because I have written this phi n c phi n, I need this minus 1 to the g. Right? Because the point was that if you had phi n c phi n, this by definition was delta n. But phi n c, right? This is just because a inner product, so you could switch them, but you have to switch their positions, right? And that requires a minus 1 to the g and delta n, right? And that's why you need this minus 1 to the g in the completeness. But this can be written as sigma 2 phi n. Okay, again this you could switch by applying an I transformation, okay? Because this is sigma 2 of 0, I dot phi n of 0. You apply an I transformation to switch them, but in that process it just absorbs minus 1 to g. And sum over m and n are implied. Okay, I have not written it explicitly. Yes.
When we do this with sigma 2 to the left side,
Yes.
means like in the case we saw that if term came for when we switch from this omega 2 to omega 1,
Yes.
and we change this, flip this from left to right, isn't that same thing?
No. See here this follows from the following fact that phi n sigma 2 is I dot phi n 0 sigma 2, right? Okay. Now I is an SLTC transform, so you can apply I on both without changing the correlation function, right? So if you do that, then that becomes phi n of 0 I dot sigma 2 of 0. Right? And now you have to just change their positions. Okay? Inside a correlation function, changing position is allowed provided you pick the appropriate minus sign if these are anti-commutative. then you will pick up a appropriate minus sign. That minus sign is this minus 1 to the g. So this is minus 1 to the g times I dot sigma 2 of 0 phi n of 0, right, which is minus 1 to the g times sigma 2 phi n. So that's all I did, right? Because these are just two-point functions on the sphere. But now you see you are in business because each of these have interpretation as correlation function on lower genus surfaces.
Like the complete set that is inserted here.
Yes.
Is in the unit space of the combined P, G, or G1 plus G2.
No. The complete set is on the sphere. The spectrum of conformal field theory. See, these are now all correlation functions on the sphere, right? So you use a complete set in the conformal field theory, right? Which are two. Their state operator correspondence is always done on the sphere. Okay. So this complete set is the usual complete set of states that we calculate from tree-level state theory, for example, right? The combined CFT of matter and forces. Okay, so let me write the integral now. So integral, I'll write this in, I'll just rearrange the various terms over here. So there will be integral dm1 1 which dm1 6g1 minus 6 plus 2n1. Okay, we are taking the first set. Okay. Then I will write this term sigma 1 phi m, which is b b1 1 b b1 because that a n1 I have replaced by phi n, because sigma 1 a n1 had that expression where the I ran from 1 to n1, right? Because I have sigma 1 with phi m, right? The a n1 I have replaced by phi m. Okay, phi m is inserted in the local coordinate system that was relevant for the n1 function. Then I write this part. Okay, because you have dq, dt bar, you can put them together. Okay, together they commute. Okay, they can be taken anywhere. Okay, you can put them again. So integral d m21 where it's d m2 6g2 minus 6 plus 2m2 d v2 1 okay, this is v1. Let me write here only. Integral dq over q, where is dq bar over q bar im v0 bar minus q l0 minus q bar l0 bar im. Let's see. Is this clear? Okay, so what I have done is I have taken the first part of the integral and I have written this part. Oh, I forgot the 2 pi I. I'll do that. Okay, I'll write it again. So I took this part of the integral, okay, and picked up the sigma 1 phi m term. Then I took the second part of the integral and picked up the sigma 2 phi n term. Okay, and then I took the third part, dq bar, q bar inverse, and I picked up this thing in the middle. And the minus 2 pi I factors will be 6 will be p minus 3 g1 plus g2 minus n1 plus n2 minus 2.
This has to be treated as a correlation function on a sphere, right?
No, now these are treated as correlation function on the genus G1 A1 surface with N1 punctures. See, this was to be treated as correlation function on a sphere, right? But this has an interpretation as a correlation function on a genus G1 A1 surface with N1 punctures, right? That is because the definition of sigma 1 is like that. So once I have rewritten in this form, right? Now these are correlation functions on genus G1 Riemann surface with N1 punctures. This is correlation function on genus G2 Riemann surface with N2 punctures. This is still a 2-point function on the sphere. Okay, but this is the usual error. Is this clear? Now you see that this part of the integral can be done irrespective of what is it they are doing. Right? Because as long as you do it for fixed m and n, right? It doesn't know about the other moduli and so on, right? So we will now do this part of the integral explicitly. So let's change variable. Let's set q as it will be minus s minus I theta, and q bar as it will be minus s plus I theta. Then dq by q becomes minus ds minus I theta, and dq bar q bar becomes minus ds plus I theta. So dq by q, where is dq bar? Over q bar becomes minus 2i ds plus d theta. So now we have minus 2i integral ds over d theta IMC. Oh, maybe I just do this. I use a minus sign here. Okay? For this, it doesn't make any difference. Okay, I use a minus sign because there are minus cubes over here. There are minus cubes over here. So B0 bar. Okay. Now the range will choose. Okay, we have glued by this plumbing fixture. Okay, so that introduces two parameters. Okay. Let's suppose that we choose the range in a convenient way. We take S to run from S0 to infinity, and theta to 0 from 0 to 2 pi. Theta is a periodic variable. In this case, in can do this integral and you get minus 2I. Theta integral gives you 2 pi. It gives you 2 pi delta L0 bar. Okay, because if L0 minus L0 bar is a non-zero, an integer, then this integral is 0. And then the S integral gives you e to the minus S naught times L naught plus L naught bar over L naught plus L naught bar. Okay, and then you have, or maybe I should have written this matrix element first. You have phi m c e to the minus S naught B0 bar. Is this okay? Okay, and notice that in this integral, I have assumed that this integral is convergent at s equal to infinity end. Otherwise, there will be a boundary term from s equal to infinity. And this, in fact, will be the definition of what this integral is. Yeah? This is, you saw it in the first lecture, that there are divergences from the boundary of the moduli space, and you have to define, okay, you have to make a choice of how you want to define the integral. Okay? And you will want to do the make the definition once and for all. Okay? And so the idea is that we will take this as the definition of the integral. Okay, that there is no boundary term from s not equal to infinity, from s equal to infinity end.
So this is just a choice that L0 plus L0 bar is positive for all.
Well, even if L0 plus L0 bar is not positive, right? Whenever you have an integral of this kind, right, which is apparently divergent from the s goes to infinity end. If L0 plus L0 bar is negative, then this is a divergent integral, right? And in the integration over the moduli space, there are such divergences. Okay, we saw it in the first lecture, if you remember, right? And we said that we have to make a definition, an analytic configuration procedure for dealing with these divergences. And the analytic configuration that we used there was precisely similar, that we had a variable s, and we said that when we do this integral, we will simply ignore the integration, the boundary term at the end. Okay, and that is then needed to get some kind of Feynman diagram interpretation. Okay. So this is the general version of that. That whenever we get a Riemann surface by gluing two other Riemann surfaces, okay, there are possible divergences from the boundary terms. Okay. And we will prescribe that those divergences are regulated by analytic continuation, okay, which in precise term means that a definition of this integral will be this. Okay, and we will see that these are the only kind of divergences that we will have in string theory, and hence once you have described how to regulate or how to analytically continue divergences, they are the boundary of the moduli space. Okay, we have defined amplitudes completely.
And this introduction of S0 is also part of the regulation?
No, S0 in fact we can remove. Okay, I will just argue shortly that S0 will choose to be 0. Okay, S0 gives a freedom, right? You are basically cutting out the moduli space because S0 is some artificial boundary of the moduli space, right? It is not covering the whole moduli space. So you still have to use some other method to do the integration over the rest of the moduli space. Okay? So how exactly to cut up the full moduli space into these parts is up to you, right? So I have chosen this S0, but often we will take S0 to be 0. Okay, the final result will not depend on the choice of S0. Now, why you have done this? Okay, and let me just mention this, and then I will stop and we will continue tomorrow. So if you look at this term, we can see that this form of the amplitude has a clear Feynman diagram interpretation. Because what is the first amplitude? The first amplitude is a genus G1 amplitude with certain number of poles, certain number of orbits or pointers, which are A1, 1 up to A1, N1 minus 1, and then there is another vortex of pattern, the spatial one, which is phi n. This is a amplitude, some G1 loop amplitude with N1 minus 1 external punctures and 1 N, which are called internal puncture, because this is not one of the external states. Then we have another amplitude, which is A21 up to A2, N2 minus 1, and then the N2th puncture is what I am calling phi. Sorry, this is phi n. This was called phi m. This is phi n. So it's a product of these two, and then this one, right? Which I have written as 1 over L0 plus L0 bar matrix element. Okay. 1 over L0 plus L0 bar has a structure of k square plus a constant. Right? Once you choose the diagonal basis, momentum eigenbasis, right, and L0 eigenbasis, this is 1 over k square plus some constant, right? So this is something like 1 over k square plus a constant is equal to Cn times An, okay, in a diagonal basis. So this is like a propagator. Okay, k is the total momentum flowing through this. You have to sum over m and n, okay, which means that you have to sum over all possible particles that can propagate in the intermediate state. Now there is also an exponential factor, e to the minus s naught times L0 plus L0 bar. But this factor you can just absorb into the vortices. Right? It's e to the minus s naught times some k square plus Cn. Square root of that you can absorb inside this vortex, and square root of that you can absorb inside this vortex, so that you get the usual Feynman propagator. Or, as you will see next time, we could alternatively simply choose S naught to be 0. Okay, if S naught is 0, then this is just 1. Okay, nothing to be absorbed in the vortex of pattern, it is just 1 over k square plus 2 Cn, k square plus Cn, which is exactly the Feynman propagator. Is this clear? So let me repeat then what we have done. We have used this plumbing fixture to generate a section of the higher genus Riemann surface, and we have not generated the whole section, we have generated part of the section, right? Because we integrated s from 0 to infinity. There are, of course, you can take s to be negative, right, which will also cover other part of the model space. So you have generated part of the section, okay, not the full integral, and that part we have shown has the interpretation of a Feynman diagram where you take these two lower genus amplitudes, okay, two lower loop amplitudes, and connect it by propagator. Connected the two.
And this is an internal propagator.
This is an internal propagator, yes, right, because this is we are summing over these things. Is this clear? And now, once we have this form, right, we can also clearly see the answer to Subramanian's question about what happens for the other kinds of fluid. Okay, when you take a Riemann surface, cut out, remove two punctures, and glue them by W1 N1, W1 N1 minus 1 equal to 2, and repeat the same story. Okay. Some of the intermediate states will, of course, change. So what will happen here is that instead of getting two products of two Riemann surfaces. You have a single Riemann surface. But now two of the punctures will be special. You will insert a phi m and phi n. Okay, at the last two punctures. And then you again glue them by this problem, this object. Right? So diagrammatic terms, what will happen is that you basically take two of these punctures as special and connect it by a finite property. Okay, it's exactly the same analysis. Okay, with a little change in the manipulations that appears in the intermediate stages. Is this clear? Yeah, and again you have to sum over all possible internal states. Okay, which will mean here that you also have integration over momentum. Right? Where internal states are labeled by momentum as well as the discrete quantum numbers. Right? So you have to integrate over momentum and the discrete quantum numbers. Here, you don't really have integration over momentum because the momentum is, by momentum conservation is fixed in terms of the other momentum of the external legs. And this is exactly what happens for a tree level graph versus a loop graph, right? This is of course not tree level, but this is one particle reducible, right? This propagator momentum is fixed by the external momentum. Okay, so here you have no momentum integration from this. Here you have a momentum integration from this. Okay. But in this analysis that we will not see this explicitly. We will see this because you have to just sum over all possible states. Okay. Are there questions?
So this momentum conservation in this, how do you see from delta A?
In this?
The momentum conservation for
That's part of the correlation definition of the correlation function. This correlation function, right, we have a total momentum concept, right? So which means the momentum that phi m carries will be determined by the momentum that this carries. Right? On the other hand, here you get a single correlation function, right? You will not have two correlation functions, but there are two phi m and phi n. Both will be inserted in the same correlation function. Right? And now the momentum of phi n are not fixed. Right? Some of the momentum is fixed, but phi m and phi n momentum are not fixed. Right? Again, you have to sum over all possible intermediate states. Sum over them will also include integration over momentum. Okay? So this is exactly what we expect in a field theory. Right? A field theory, but a field theory with infinite number of fields, right? Because the sum over m and n are over infinite number of states, right? Infinite number of discrete quantum numbers, and in this particular case, when you have two punctures on the same Riemann surface, also integration over the internal momentum. Okay, so tomorrow then we will try to use this insight to see how the full moduli space can be built from Feynman diagrams. Right? This is just one example, right? That here what I have shown is that if we take a plumbing fixture, right, which is a very special case of two Riemann surfaces joined together, then the amplitude that we get from there can be reinterpreted as two amplitudes joined by an internal propagator. Okay, but then we will try to use this insight to see how the full moduli space that we have to integrate over can be thought of as a sum of Feynman diagrams. Okay, and from there we can reconstruct the string field theory whose Feynman rules will produce those Feynman diagrams. Okay, so here the way we are proceeding is reverse of what we normally do in a field theory. Right? In a field theory, you start a Lagrange with a Lagrangian and then you derive the Feynman rules, right? Okay, in string theory you know the amplitude, right? And you are trying to go backwards, starting from the amplitude, we are trying to reinterpret first as a sum of Feynman diagrams, and then we will try to discover a field theory whose Feynman rules will give you those Feynman